pleased to introduce the speaker for this session, Tristan Burton. Dr. Burton has 28 years of experience in computational fluid dynamics in a wide variety of application areas, including multiphase flows, two-stroke engine breathing, and conjugate heat transfer. He began his career on the faculty at the U.S. Naval Academy, teaching fluid mechanics for engineering majors and thermodynamics for English majors, and then transitioned to engine CFD at a pair of startup companies. In 2015, Dr. Burton joined Convergent Science as employee number 1 at the Detroit office, where he led sales and technical support efforts before transitioning into his current role in 2019. He received his Ph.D. in mechanical engineering in 2003 at Stanford University. It will now be our pleasure to hear from Tristan Burton.
Thank you for the introduction, and thank you to those of you in the audience who are attending this talk. This is work that's been done by myself and other collaborators listed on the title slide here at Convergent Science. And we're talking about the simulation multiverse. And the first question is, what do you mean by the simulation multiverse? We've probably heard the word multiverse recently in the context of the Neil deGrasse Tyson remake of Cosmos, or even the Marvel Universe movies that have been so popular lately. I'm talking about something a little bit different. I'm talking about the simulation of problems with multiple scales, both length and time scales, multiple conditions, meaning do we want to investigate how things depend on various properties, multiple phases, in this case, liquid, gas, or solid, multiphysics, simulating different physical phenomena together in one simulation, and multiple realizations, where we actually have behavior that requires that we run multiple simulations of the same set of conditions in order to extract statistical information. And all of these things can be enabled with the use of multiple cores. These allow us to access larger amounts of compute resources and address more challenging problems. I began the journey into the simulation multiverse a while back. You may have heard the joke that people say college was the best 7 years of their lives. For me, college was 11 years of my life. I went to graduate school in a very warm place, and that's unfortunately a blessing and a curse in that you are not motivated to finish as early as you might want to otherwise. But at a certain point, I asked what did I have to do to leave? And these were my graduation requirements back in 2003 when I finished up my graduate work. I had to do fully resolved simulations of particle-laden turbulent flow. And this problem encompasses some of the items listed on the previous slide. We've got multiphase flow, a solid particle surrounded by a fluid. We've got multiple scales. Turbulence is sort of one of the canonical multi-scale problems in that you have a range of fluid motions going from the smallest scales where viscosity is active up to the largest scales that are on the size of your flow domain. And I had to do a statistical analysis because depending on where I put my particle in this turbulent flow, I would get a different result. As a result, I had multiple realizations of the same simulation effectively. Now, back at the time, compute resources were not as readily available as they are now. And so I was running on each one of these simulations on only 9 cores. And each one of those simulations took a few weeks. So you put that all together for 64 realizations, a few weeks each. You're talking about years of simulation time in order for me to be able to graduate. A word on the mathematics involved in simulating the multiverse. And I wanted to keep this at a relatively high level, so I stuck to Twitter for the mathematics. On the left, we see sort of the standard progression of our mathematical abilities going up starting from numbers and counting in elementary school, working our way up through advanced calculus, maybe in college, and then if we are in the field of computational mathematics, we'll go a step further and go to numerical methods, which allow us to solve some of these advanced calculus problems on a computer. But there's another wrinkle that gets added to this as you increase the complexity of simulations, which is what happens when you have multi-physics applications. You start to lose the determinism. You start to get stochastic behavior. A simulation that is arguably the same may produce different results. This is sort of a transition from order to chaos. And then we need to start thinking like a statistician. What that means in many cases is that we assume there's some sort of Gaussian distribution of the underlying physics, and then we are able to use that assumption to calculate some averages and properties that we can use to help us in our engineering work. Now, what do we need to participate in the simulation multiverse? We need some software that can accurately capture whatever problem we are working on, the phases, the physics, and the length and timescales. Then we need access to hardware, preferably scalable on-demand hardware, so we don't need to have it on site. We can just turn it on when we need it and turn it off when we don't. And we may want some sort of low latency interconnect, meaning that the communication between the cores is relatively fast. Depending on our problem physics, if communication is limiting everything, then that low latency interconnect can allow us to reduce the turnaround times. And it's always a benefit to not have to have our in-house IT team maintain it. So if this is housed at somebody else's facility and they maintain it, that would be great. And now a word from our sponsor, in this case, my sponsor, which is Convergent Science and our software, Converge CFD. One of the things we talk about when we look at computational fluid dynamics problems is the validity of our results. And the validity of the results will depend on the resolution which is provided by the mesh upon which the continuous transport equations are discretized. This is how we convert a continuous problem into a discrete problem that can be solved on a computer. We have a mesh that allows us to change those equations from continuous to discrete. But the question always arises, if you change your mesh, will it change your answer? Because if that's the case, then you may not be looking at the answer you want. You may be looking at an artifact of the mesh that you selected. Now, I'm old enough that I remember a time when people used to insult one another by saying that sometime in the past called and they want their X back, indicating that somebody's out of date. But in this case, 2008 called was when Converge was available for sale. They don't want their meshes back. What they want is autonomous meshing, meaning the computer will build the mesh for you. So in Converge, we assemble a base grid, which is just a uniform Cartesian mesh that fits around everything. We may add some local embedding to capture gradients of physical properties around solid boundaries or wherever there's interesting physics going on. But this is all static. For complex problems, what we need is a dynamic meshing strategy. So what I'm showing on the right is sort of the final step in our meshing strategy, which is known as adaptive mesh refinement, where the solver itself calculates on the fly how much mesh should I add and where should I add it. So what I'm showing here is a jet in crossflow, and you can see the gradients are leading to the code adding more cells to capture those gradients in a dynamic way. If we were to try and capture this with a uniform mesh, we would have a far greater number of cells than we have with this adaptive mesh refinement. So this is a way for us to basically guarantee that we get the maximum accuracy for the minimum cell count cost. There's a number of problems we can address with this type of strategy. The first one I'd like to talk about is fluid structure interaction. And this is basically usually a solid body of some kind being moved by and also influencing a fluid that surrounds it in some way. Now in Converge, the simulation preparation for this moving body problem is identical to a fixed boundary problem because the Converge makes the mesh dynamically. So it's no more difficult for you to set this problem up than a problem without motion of a solid boundary. And the simulation down below shows a boat hull moving through some waves. And you can see sort of the boat moving up and down with the waves. You can see the mesh being added locally where there are gradients around the hull. And so this problem addresses three of our sort of clouds from the initial slide. We've got multiple scales in all the fluid scales. We've got multiple phases. We've got a liquid and a gas. And we've got multiple physics, which in this case is basically Newton's laws for the fluid and Newton's laws for the hull. And we can sort of get the interaction between the hull and the fluid using this strategy. A more perhaps interesting example of fluid structure interaction is the capping stack. So on the right, I'm showing a picture of a capping stack, which is an object which is an oil well blowout contingency device. You may remember this from the Deepwater Horizon accident of 2010, when the wellhead was spewing oil and gas into the Gulf of Mexico for many months. And to fix that problem would have been to position a capping stack over the wellhead. The capping stack is basically hung from a cable down to the seafloor, and you need to position it over the riser coming out of the well, and then shut off the oil and gas which is flowing freely into the ocean. Now, this presents some challenges. It's rather difficult to position a 20 foot by 20 foot by 20 foot, 105 ton object over a sort of 1 to 2 foot pipe at a depth of thousands of feet. So I asked the question here, sort of what could go wrong? And of course, we did see what went wrong. In that case, the attempts to position the capping stack failed, and the riser coming out of the seafloor was damaged, and they were unable to put a capping stack on top after the riser was damaged. So we can simulate this to understand how difficult it is to sort of move the capping stack into position. So we're running a fluid structure interaction here. We've got the cable moving up at the surface, and then the capping stack down at the depth follows it. And we sort of move it over the wellhead and then position it on top of the wellhead. And finally, once it is locked into position, we can shut off the flow of oil and gas by closing the valves in the capping stack. So this is an example of something that would be very difficult to experimentally investigate. We can do it in simulation to sort of look at how difficult it is to control positioning of this capping stack. Now, there's been a move, obviously, lately away from sort of fossil fuel energy towards renewable energy. There's a large number of problems in the renewable energy space that have many of these features, multiple physics, multiple scales. So here's a prime example of one, is wind turbine modeling. So if we think about a wind turbine, we can think about the smallest scales of interest, or maybe the small fluid scales around the wind turbine blades. And we sort of move away from there to sort of the size of a wind turbine in its entirety, which may be 100 meters in diameter, something of that order. And then, we sort of position those wind turbines individually within a wind farm. And then we may be interested in the meteorological conditions which lead to a favorable location for a wind farm. And those occur over much larger distances, maybe hundreds of kilometers. Now, computational fluid dynamics works in this middle of this band, sort of a few millimeters to maybe a few meters. But there's a need to basically transmit information from those scales to the larger scales so that we can decide where to site a wind farm and what the sort of the power production might be. Offshore wind energy in the US, it's estimated there's about 7,200 terawatt hours available in US waters. I think in the last few years, the US has probably used about 4,000 terawatt hours of total electricity. So there's plenty of wind energy out there that's ripe for utilization. And there's a variety of interesting physics. We've got atmospheric turbulence, we've got the waves, we've got the blades that may deform. You've seen these blades, they are flexible to some degree, and so they do experience deformation as a result of the wind loads. And then in the case of the wind farm, we've got the wakes from one wind turbine interacting with the next wind turbine and maybe decreasing its power. So just to give you a concept of scale here on the evolution of the wind turbine, we're currently pushing 200 meters in the height of the wind turbine tower. It's going up rapidly, and this requires at a certain point, if you want to run a CFD simulation of that, the size of the domain required to even include a single wind turbine will become problematic. And so at that point, we may need to resort to some models, which I'll talk about in the next slides. All right, if we want to simulate wind energy production, we need an accurate representation of the environmental flow that produces that wind energy. So we need a way to set this environmental flow up correctly in our simulation. And this may incorporate a number of different features. There's some type of wave pattern with some type of spectrum that is interacting with the wind turbine, whether it's a fixed bottom turbine or a floating turbine. There's a wind profile. And part of the reason the towers keep getting taller for the wind turbines is that at higher altitudes, you get a more uniform stream of air moving across the wind turbine. So we look at our plot, our movie down here, we can see that the velocity as we move up away from the surface of the water goes up pretty quickly. And once we get up to a high enough distance, it becomes more uniform. So we get a relatively uniform stream of air at a higher altitude. There's always the presence of turbulence in these problems, both in the gas and the liquid. And so we need to incorporate those effects if we want to get accurate predictions of the wind energy that will be produced. All right, so we'll start with the easy version of the problem, which is a fixed bottom wind farm. So these are still offshore, but they're in shallow enough water so they can be secured to the seafloor. And an example of this is the Lillgrund offshore wind farm. And as I mentioned, the size of these turbines is getting relatively large so that we may have to sacrifice some accuracy on the small scales. And so what we actually do here is simplify the problem a little and run a rotating actuator disk model instead of trying to resolve around all the details around each blade. But we include the effects of synthetic turbulence. You can see in the lower left there the impact that has when we include synthetic turbulence versus without synthetic turbulence. So the one in the right-hand side of that image pair is a far more accurate representation. On the right-hand side, we're showing some of the comparisons of our simulation work with the reference in the literature, and they both show they show close agreement with the work that was in the literature. Now, the more difficult problem is the floating offshore wind turbine. And so when we talk about simulating a floating offshore wind turbine, we're talking about a 6 degree of freedom fluid structure interaction problem. The floating offshore wind turbine can move in all 3 coordinate directions, and it can rotate around all 3 coordinate axes. You've got the interaction of aerodynamic loads, hydrodynamic loads, and also the mooring forces from the cable all sort of working together. When we combine this into our simulation, we get a depiction of what will happen to the wind turbine when it is exposed to the prescribed wind load and also the prescribed wave spectrum. And so we may decide that we need to adjust our mooring tension in order to prevent these movements of the wind turbine, which would probably reduce power production. All right, the second area that I wanted to talk about today that involves many of these multiverse phenomena is conjugate heat transfer. Now, in conjugate heat transfer, one of the big differentiators there is that there's a timescale disparity in that the solid will respond very slowly to whatever you're using to cool it. And so we can take advantage of that in certain conditions. So we can fix the flow because we know that the flow changes very, very fast and the solid changes very, very slow. So this is a way we can sort of accelerate our simulation and maybe not spend as much time running the simulation. So we've got a battery pack module here. This is just a warm-up simulation, meaning we run current through the battery pack, and there's coolant passages on the left and right, coolant supply on the right, coolant return on the left, and there are thin fins in between each pair of cells that carry the coolant between the batteries and carry some of the heat away. So this problem now incorporates multiple scales, multiple phases, and multiphysics, just like we had before, but now we're going to add multiple conditions, meaning what coolant flow rate will actually allow me to keep my battery temperature at a prescribed value. And then we're also going to add multiple realizations to this as we incorporate some of the complex physics of lithium-ion battery chemistry. So lithium-ion batteries undergo something known as thermal runaway, and this is a result of adding chemistry to the problem. When the battery reaches a certain temperature, internal chemical reactions will produce self-heating, and at that point, you can't shut it down. And this may be due to mechanical abuse, meaning a nail penetration event, operational abuse, maybe it was being cycled, charged and discharged too quickly, or maybe even thermal abuse, it's just too hot. And we can try and mitigate this with coolant and insulation, but under certain conditions, once it reaches that sort of temperature threshold, there's not much you can do. The simulation shown in the bottom of the slide is a thermal runaway and venting simulation, because after the thermal runaway occurs inside each battery cell, it will vent the gases from the cell into the surrounding battery pack. And this may then lead to propagation of the thermal runaway to other cells, which is what leads to the spectacular battery fires you may have seen circulating on social media. Now, I mentioned that this problem requires multiple realizations. So this is some experimental work done by Peng Zhao at the University of Tennessee, where he took the same battery exactly type from the same batch and put them in an accelerated rate calorimeter, which is basically an oven, heated them up and looked at the response. And what he saw is that the temperature response of these cells was widely different in that it could go into the thermal runaway as shown by the spikes in the image. You can see that they happen thousands of seconds apart. So this is something that may indicate that we need to do a statistical analysis of this problem. So we looked at this in Converge using a species perturbation study, meaning we initialize the species throughout the battery slightly differently from case to case to see whether or not we can get different thermal runaway behavior. And indeed we can. You can see the temperature response in the middle graph there on the right. you can see one of those cells went off much earlier than the others. And so from this, we can calculate something like a confidence interval like we have in the plot in the lower right-hand corner, which basically gives us a mean response of the battery cell and sort of some bands around what we might expect in terms of the variability of that response. All right, a quick word on scalability. Everybody wants to see linear scaling. I put here in the slide, linear scaling for multiphysics problems only occurs in other universes. It never occurs in ours because while the plot on the right is nice to show, it's not representative of real multiphysics problems. If we go to a multiphysics problem like an oil-cooled motor simulation, we have far greater complexity of the interaction between the physics. What this means is that you will probably not expect linear scalability from a multiphysics type simulation. So just a word of caution, the linear scaling is only for simple problems usually that have just one set of physics. All right, some final thoughts. With great power comes great responsibility. Getting back to the Marvel universe I mentioned earlier. Core hours are easier than ever to burn, but we're hoping to produce more than heat. So we want to use those cores efficiently to get accurate simulation results. And more and improved hardware, while it enhances our algorithms, it's not a substitute for improving our algorithms. There's a lot we can do algorithmically to reduce the computational expense. And the last thought is it's a good idea to let computers do what they're good at. So in this case, using Converge to let the computer build the mesh is a good thing because there are very few of us out there who enjoy building meshes. With that, I'll thank you for your time and finish this presentation.